This lesson is on independence and tests for independence. Two events are independent if the occurrence of one does not affect the probability of the occurrence of the other. You can test if variables are independent of each other using conditional probability. Take, for example, the drawing of two cards, once with replacement and once without. Find the probability of drawing a jack, replacing the card, and drawing a jack. So the probability of getting a jack and a jack is equal to the probability of getting the first jack times the probability of getting the second jack. In this example, it does state that we are replacing the card. So the probability of getting our first jack would be the 52 cards we have in our deck, 4 of them are jacks, times the probability of the second jack. There are still going to be 52 cards in our deck because we replaced the original card that we had pulled out, and of the 52, 4 of them are still jacks. 4 times 4 is 16 over 52 times 52, which reduces to 1 out of 169. These events would be independent of one another because the probability of one event did not affect the probability of the other. Our second example. Find the probability of drawing a jack, not replacing the card, and drawing a jack. So this is also the probability of drawing a jack and drawing another jack. However, I'm going to notate this is jack 1 and this is jack 2. This would be the probability of jack 1 times the probability of jack 2, given we had already pulled out a jack. This probability would be, of the 52 cards, 4 of them are still jacks in our deck. If we assumed that we had not replaced the card, then I'm going to state that I only have 51 cards left in my deck. And of the 51 cards, I would only have 3 jacks left in my deck. Multiply straight across, 12 over 2652 reduces to 1 over 221. Because the probability of drawing our second jack was affected by us pulling out a jack initially, these two events would be dependent of one another. In our first example, the probability of both events A and B occurring was equal to the probability of event A times the probability of event B. For our second example, the probability of both A and B occurring was equal to the probability of A times the probability of B, given A had already occurred. In other words, the probability of jack times the probability of pulling a second jack, given we had already pulled our first jack. Therefore, independent events have the following equations. We can use a multiplication test in order to determine whether or not our two events are independent. This would be using the probability of A and B being equal to the probability of A times the probability of B. Another way that we can test for independence would be using a conditional test. If we know that the multiplication property proves independence, and if the probability of B given A ends up being the same as the probability of B, that's actually another way that we're able to prove independence, and that's the conditional test. The probability of B given A being equal to simply just the probability of B would mean that A and B are independent events. We can use these equations as our tests for independence. We'll go through some examples together. We have a two-way table, and our first question for example 1 is having pierced ears independent of being a male? We can either use the multiplication property or we can use a conditional in order to determine whether or not they are independent. For this, I want to identify what my events are: pierced ears and being male. So is the probability of having pierced ears and being male equal to the probability of having pierced ears times the probability of being male? If these two are equivalent to one another, then I can state that these two events are independent. Using my two-way table, the probability of pierced ears and male would be the intersection of pierced ears and male. That would happen in this box. There are 19 out of a total of 178 that are both male as well as having pierced ears. Then I'm going to also find the probability of just having pierced ears. There is a total of 103 out of the 178 who have pierced ears. The probability that someone in this survey was male would be 90 out of 178. I'm going to multiply these two probabilities together and see if it ends up being equal to the intersection of pierced ears and male. The probability would be 0.1067. Pierced ears and male would be 0.2926. Because these two are not equal to one another, I would conclude no, pierced ears and male are not independent. Because we use the multiplication property to answer letter A, for letter B, the other test would be the conditional test. Is the probability of having pierced ears equal to the probability of pierced ears given male? The probability someone just has pierced ears would be 103 out of 178. Given male means that we are looking at the 90 total males that we have. And of the 90, the probability that they have pierced ears was 19 out of the 90. These two probabilities are not equal to one another. Therefore, we can also conclude that pierced ears and male are not independent. Let's take a look at example number 2. This is a 3x3 table. By school, it's referring to what major they are a part of at their college. Then along the columns, you see the grade averages of these students. Perform and interpret a few tests for independence. What's missing from this table are the totals. This question is unclear in which events we are trying to determine are independent of one another. Are we trying to determine whether liberal arts and having a B average are independent, or are we trying to determine whether or not the school that you're part of as well as your grade average are independent? Let's assume that we're trying to determine the independence of school and grade. However, in order to determine if that's true, we would have to test all the different categories against one another and determine if all of them are independent of each other. There are many different answers that you can come up with for this question. To start off with, I'm just going to determine what is the probability that some student has an A on this campus. The probability of A would be of the 10,000 students that are part of this survey, 3,392 students have an A average. This is equal to 0.3392. The conditional test seems to make the most sense here, so I'm going to compare this probability to the probability of having an A given that you are in the Health and Human Services school. There are a total of 2,100 students in the Health and Human Services, and of those, 882 of them have an A average. This would be approximately 0.42. Now immediately I can already determine that since these two are not equal to one another, school and grade are not independent, and I can be done. If I wanted to just kind of see what all the different probabilities would be, I can do a couple more tests out of curiosity. What is the probability of having an A average given that they are part of the engineering school? Well, there are a total of 1,600 students in the engineering school, and 368 of them have an A average. This is approximately 0.23. So it does appear that this average is lower. And lastly, the probability of having an A given that you are part of the liberal arts school. This is equal to, of the 6,300 students in the liberal arts School, 2142 of them have an A average, which is approximately 0.34. At this point, we can conclude, no, school and GPA are not independent. Three, draw a Venn diagram that shows two independent events. We can use either the conditional test or we can use multiplication in order to answer this question. When we learned Venn diagrams, it was a lot easier to see the intersection of the two events A and B, which is why for this particular example, I would probably use the multiplication property to answer this question. The probability of both A and B occurring would equal the probability of A times the probability of B if the two events are independent. So your goal right now is to determine if the entire sample is 1. As a proportion, are you able to fill in what the intersection is as well as the rest of the Venn diagram, including the complement, to determine what numbers could work to make this equation true? I would like you to try that out on your own and be prepared to share that in conference next class. Part B, two dependent events. It's a similar idea where you have two events, A and B. However, for the probability of A and B occurring, the intersection is not going to equal the probability of A times the probability of B. If you can also fill in the rest of the information for the Venn diagram to make sure that these two are not equal to one another. 4. Back to the chickenpox data. This comes directly from the conditional probability lesson. Show using conditional probability and explain your results using a few sentences. Gender and having the chickenpox are either dependent or independent. Conditional probability is the probability of B being equal to the probability of B given A, or the probability of A being equal to the probability of A given B. The probability for having the chickenpox is equal to 80 out of the total 500 people. This is equal to 0.16. The probability of having the chickenpox given female is equal to, there are 200 females total. Of the 200, 30 of them have chickenpox, which is 0.15. Because the probability of having chickenpox is not equal to the probability of having chickenpox given female, we would conclude that these two are not independent of one another. Letter B, you're asked to do the same example. You can choose whatever events that you want within this. However, we'll just be consistent and check the other gender. The probability of having chickenpox we already found from the previous example as 0.16. The probability of having chickenpox given male. There are a total of 300 men in this study, and of the 300 of them, 50 had the chickenpox. 50 out of 300 is equal to 0.16 repeating. Like we saw in the previous example, the probability of having chickenpox is not equal to the probability of having the chickenpox given male. So therefore, we conclude that these two are dependent. Show using the multiplication property and explain your results using a few sentences. The multiplication property would be the probability of both A and B occurring is equal to the probability of A times the probability of B. The probability of male and chickenpox is equal to the probability of male times the probability of chickenpox. We want to see if these two are equal to one another. The probability of male and chickenpox would be the intersection, so 50 out of the total 500, which is equal to 0.1. The probability of male, which is 300 out of 500, times the probability of chickenpox, which is 80 out of 500, gives us a probability of 0.096. Because 0.096 is not equal to 0.1, again, we will conclude that they are not independent. And the very last example, the probability of female and chickenpox is equal to the probability of female times the probability of chickenpox. The intersection of female and chickenpox would be 30 out of the total 500, which is 0.06. Is this equal to the probability of female, which is 200 out of 500, times the probability of chickenpox? This probability is equal to 0.064. Because it is not equal to 0.06, again, we conclude that they are not independent. Please use the two-way table to find the probabilities in question 5, letters A through D. Pause the video at this time and check your answers in the next slide. For our last example, are being female and participating in an after-school athletic program independent or dependent? So the two events that we're looking at would be female and participation in our after-school program. Show two different ways you can find your answer: conditional probability and multiplication property. Please note that this question is not asking, is gender independent of participation in after-school athletic programs? If that were the case, then we would have to check many other probabilities. I would have to check males and participation, males and not participation, females and participation, females and not participation. Because we are specifically being asked females and participation, we only have to check for those two. Please pause the video at this time and use both tests for independence to see whether or not females and participation in our after-school athletic program are independent. The answer is that female and participation in after-school athletic programs are independent because of both the multiplication test for independence as well as the conditional test.